Once again, you're welcome to waidusmacademy. Today we'll be looking at the industrial manufacture of ammonia, and the process that is used in the industry for manufacturing ammonia is called the Harber process. The process that is used in the industry for manufacturing ammonia is called the Harber process. So before we elucidate the process of the Harber process itself, before we look at it, let's quickly take a look at this tutorial.
This video is about the Harber process. Ammonia is produced in the Harber process from hydrogen, which is obtained from methane, and nitrogen, which is obtained from the air. Nitrogen and hydrogen enter a compressor, where they are compressed and pumped into a reaction vessel. The conditions inside the vessel are a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an ion catalyst is used. Some of the nitrogen and hydrogen react to form ammonia, and an equilibrium is established between the three gases, as shown in this equation. The forward reaction is exothermic, and the reverse reaction is endothermic. The reaction mixture leaving the reaction vessel, which contains a mixture of all three gases, is cooled. Ammonia has a higher boiling point, so it condenses, and liquid ammonia is removed. Nitrogen and hydrogen remain as gases, and they are recycled back into the reaction vessel. Make sure you learn these reaction conditions. As the Harber process is a reversible reaction, the position of equilibrium, and therefore the yield of ammonia, can be altered by changing the conditions, as shown in this graph. We can use Le Chatelier's principle to predict the conditions that would favour the highest yield of ammonia by favouring the forward reaction or shifting equilibrium to the right. However, other factors need to be taken into consideration. Let's look at each condition in turn to explain why it is chosen. A lower temperature would favour the forward reaction, as it is exothermic, and the graph shows how the yield of ammonia increases as the temperature decreases. However, at lower temperatures the rate of reaction is slower, so a compromised temperature of 450 degrees Celsius is used, which gives a lower yield, but it is made more quickly. To explain the pressure conditions, we need to think about the number of molecules either side of the reaction. As there are more molecules on the left than the right side of the equation, a higher pressure will favour the forward reaction. And again, we can see the increase in yield of ammonia as the pressure increases on the graph. However, the equipment needed to withstand very high pressures is expensive, and high pressures are dangerous. So 200 atmospheres is used as a compromise between yield and cost and safety. An ion catalyst does not affect the position of equilibrium, but it increases the rate at which it is obtained, and a lower temperature can be used. You need to be able to explain the compromise between rate, yield, cost, and safety of the conditions used. Exam questions about the Harber process often test your recall of the equation and the conditions used. This question focuses on the reaction conditions. Part A asks you why a high temperature is not used, even though it gives a faster rate of reaction. Whenever explaining the temperature conditions of a reaction in an equilibrium, you always need to explain that higher temperatures favour the endothermic reaction, and you need to identify which direction is endothermic. In this reaction, you were told that the forward reaction is exothermic. Therefore, the reverse reaction must be endothermic. You could also say that the left-hand side or the reactant side is favoured. For the third mark, you need to give a reason why this is not desirable, and that is because the yield of ammonia would be reduced. Part B asks what would happen to the unreacted nitrogen and hydrogen when it leaves the reaction chamber. The gases are fed back into the reaction vessel, where they pass over the catalyst again, so they are recycled. Another accepted response is to say they are used again. In summary, ammonia is produced in the Harber process from hydrogen, which is obtained from methane, and nitrogen, which is obtained from the air. The equation for the reaction is shown here. Typical conditions used in the Harber process are a temperature of 450 degrees Celsius, a pressure of 200 200 atmospheres and an ion catalyst. The temperature used is a compromise between the yield and the rate. The pressure used is a compromise between yield and cost and safety. Don't forget to check out all our other fantastic revisions.
Okay, so that's the first part, and we're going to take this Harber process in 5 stages. What is happening in the 5 stages? Okay, we've shown you, you can see the diagram. This is the diagram of Harber process in the industrial manufacturing of ammonia. So to make ammonia, we need 2 reactants. We need 2 basic reactants, 2 major raw materials, which are the hydrogen and the nitrogen. The nitrogen we get from the air, and the hydrogen we get from methane gas. Okay, so when we get these 2 materials, we have built an industrial machine that has different stages, and these 5 stages are incorporated in this diagram, which we're going to describe. The first is to get the source of the material, raw materials, the gas that we're going to pump into the compressor. So the first is pumping the raw material, the gases, the nitrogen from the air and the hydrogen from the natural gas. Pumping them into the compressor is the first stage in the making of the ammonia using the Harber process in the industry. So that's our stage 1. So stage 1 is the hydrogen and nitrogen that we obtain from natural gas. Remember, we get the hydrogen from the natural gas, from methane specifically, and we get the nitrogen from the air, and we pump them to the compressor through the pipes. These are pipes. So you can see nitrogen from air here, you pump through the pipe, and the hydrogen from the natural gas, the methane natural gas, so they get mixed up. So like the first stage is to find how to mix the 2 gases, nitrogen and hydrogen. So we mix them. So, and then we pump them to the compressor. So compressor will compress the 2 gases together, like grind them together. The compressor will scrub them together. We mix them and scrub them and clean them. Okay, then the gas mixture is compressed here at this stage 2. That's our stage 2. The gas mixture is compressed at stage 2. The gases are compressed to about 200 degree atmosphere. 200 atmospheric pressure in the compressor. Here we make the pressure available in the compressor to be 200 atmosphere. 200 atmosphere is 20,000 kilopascal. 200 atmosphere. This is okay, just a moment. 200 atmosphere ATM. 200 atmosphere. This is the pressure. So we make the pressure in the compressor to be 200 atmosphere. 200 atmosphere is to multiply with 100,000. This will be is equivalent to 20,000 kilopascal. This is equivalent to 20,000 kilopascal. Kilopascal, not pascal. 20,000 kilopascal. So if you want to change to pascal, this will be what? This will be 20 million. This will be 20 million. If you want to change to pascal, this will be 20 million pascal. This is the value, because you have to add another 30 to this 20,000 if you are changing to pascal. If you remove it from kilo means times 10 to the power of 3, which is 1,000. Kilo means 1,000 of whatever you're saying. Okay, so this is 20 million pascal. This 200 atmosphere. Okay, so we are saying the pressure. This is a trade-off, that the pressure should not be too high. 200 atmosphere is okay. You know, the pressure can be higher, but when you increase the pressure, the yield of ammonia reduces. The yield will decrease. So this is a very vital consideration for this case. So we say here the compressor has to be the compressor. Stage 1 is to pump the gases, pumping into the compressor, pumping the gases. What are the reactant gases? The reactive gases are nitrogen and hydrogen. Pumping hydrogen, and nitrogen into the compressor. That's the first stage. Pumping hydrogen and nitrogen to the compressor. Okay, so I will just say pumping hydrogen and nitrogen. Okay, that's stage 1 in the Harber process. Then, in the Harber process, the second stage is the compressor, the job it does. The gas mixture is compressed. Compressing the mixture of gases. That's what is happening here. Compressing the mixture of gas. These two gases, you compress them, okay? So compressing the mixture is the second stage. Compressing the mixture. So we're going to show you from the diagram. Compressing the mixture is the second stage in the Harber process. So these two gases have to be compressed, meaning you have to scrub them, you have to clean them, you have to scrub them, you have to mix them properly. Okay, you compress them so that they mix absolutely well. Okay, so that's our second stage, and that stage is shown in the Harber process here. Let's show it. Where is the compressing taking place here? This stage. This is the compressing stage, stage 2. So this is where the gas will be mixed properly. When they mix, then they send to the converter where the reaction will take place. In the converter, stage 3, the gases are sent to the converter. So in stage 3, the compressed gas flow to the converter. So that's where the reaction will now take place. The making of the ammonia takes place. So a round tank with beds of hot iron. Iron is used as a catalyst. Hot iron, 450 degrees, is used to catalyze the forward reversible reaction. So what we have here, what we see here, is that the third stage, we have what? The gases sent to the converter. So I'm trying to summarize it so that you know what is happening. Here, stage 3 is just a converter sent to converter, and then they react to produce ammonia. These gases sent to the converter to convert them to ammonia. Converter, from the name, as the name implies, the job of the converter is to convert the hydrogen and nitrogen gas to form ammonia. Meaning, this is where the reaction takes place. Okay, here we can write the equation. We can write the equation for the reaction because this is where the whole thing is taking place, right? This is where the whole thing is taking place. So we can simply write the equation for the reaction as stage 3. So as stage 3, we can simply write the equation. We say nitrogen react. Nitrogen is a gas. Okay, nitrogen react with. You have to put the state symbol. It's a gas, so we put gas. Nitrogen as a gas. React with. React means plus. Hydrogen. The hydrogen is got it from methane, from natural gas. Okay, the nitrogen is got it from the air. So these two, you must know where they obtain from. Okay, these two reactants or raw materials. So it's a reversible reaction. So it has a forward reaction and it has a backward reaction. It's a reversible reaction, meaning equilibrium can be reached. To produce ammonia. NH3. So we can balance the equation as it were. Because here on the right side, nitrogen is 2. On the left, nitrogen is also 2. So right here, nitrogen is 2 because 2 times 1 is 2. And here, nitrogen is also 2. So nitrogen is balanced. The hydrogen is not balanced. Hydrogen on the right side is 2 multiplied by 3, which is 6. But here is 3, is 2. On the left is 2. So we have to put 3 here. We have to change the color to put 3 here. So we put 3 here to balance the hydrogen atoms on the left. So this is what is happening. The forward reaction, what favors the forward reaction? We're going to talk about these conditions, and what favors the backward reaction. So in the converter, what happens? These two gases are converted to produce ammonia. They are converted to produce ammonia. So we take a look at it. We take a look at it as it's happening. Okay, here there are beds. You look at these things like step. They call beds of iron. Iron bed. You can call them iron bed. Iron beds. Okay, these iron bed, they act as what? Catalyst. They act as what? Catalyst. The catalyst. The job of a catalyst is to speed up the rate of reaction to make the reaction happen faster, but it's not itself a part of the reactant. It's not used up in the reaction. Okay, its job of a catalyst is the iron is used as a catalyst in Harber process in terms of making ammonia. Iron is used as a catalyst, and is seen here as a catalyst. It's used here as a catalyst. Sorry, okay, it's used here as a catalyst, and then when that happens, it produces ammonia. Now, this ammonia that is produced is cooled, is sent to a cooling tank. That's step 4. Step 4 is that the ammonia that is produced in stage 3 is sent to a cooling tank. Ammonia number 4. We say the mixture is cooled until ammonia is condensed to liquid. Okay, so cooling in order for the ammonia to be condensed to a liquid. Cooling. Step 4 is cooling. Step 4 is cooling. Okay, cooling in order for us to get what? In order for us to get liquid ammonia. In order for us to get liquid ammonia. You cool this one that is produced, you cool it, the mixture of the two gases that is producing the ammonia, you cool them so that you can get what we call the liquid ammonia. Once you get liquid ammonia, they will tell you what will happen. Okay, the ammonia will be sent out to another tank where it will be obtained. Okay, the ammonia that's produced. Mind you, the ammonia that's produced is always around 50%, it's not much. Okay, but what then happened to the hydrogen and nitrogen that didn't produce the ammonia? They are set back to the converter in order to continuously produce, set back to produce step 3 and step 4. Okay, so here liquid ammonia is obtained and is sent out. So before we talk about step 5, let's go back to the diagram. So here, this is the converter. The converter produces what? It produces liquid ammonia, and it's set for cooling tank to cool down. You know, it's very hot. It's very hot. So to cool, the cooled one becomes liquid ammonia. Because you know when something is cooling, it changes from gas to liquid. If you cool further from liquid, it will change to solid. So we cool it here to reduce it from being gaseous to liquid. And then here we collect the ammonia out. We send to another tank where we collect the ammonia. But what happens? We say only 50%, 15% forms the ammonia. So there's 85% still left of the hydrogen and nitrogen that didn't form ammonia. So what we do to them, we design this system to be like a feedback. So the nitrogen and hydrogen that didn't form the ammonia is again sent back to the converter. See, through this place. It's sent back through the converter through this pipe to the converter to make ammonia again. It's a continuous process. So we get 50%, we take the ammonia out after cooling, then the remaining hydrogen and nitrogen that didn't form is again through the pipe sent back to the converter. So it's going to be step 3 and 4 will constantly and continuously be repeating itself. So now quickly let's take a look at the condition affecting the Harber process. Okay, before we talk about the condition, step 5, we've not reached the step 5. So what is happening in step 5? The ammonia is obtained, right? So step 5, we say the ammonia is run into a tank and stored as a liquid ammonia. Okay, so ammonia is stored. Ammonia obtained is stored, right? So we get the ammonia. Remember the ammonia we get is a liquid one. It's cooled. So it's not a liquid ammonia. So we store it. We store the ammonia. And we repeat step 3 and step 4 again to produce more ammonia and store. And send to a tank to store. So we can say here is this store is a tank. Here is a tank. Here is a tank. Here is a tank. So we store it. So we repeat step 3 and 4 again. Step 3 and 4, we repeat them again in order to produce more ammonia. Why? Because only 50%, only 50% ammonia is produced from this process. So the remaining 85% for the hydrogen and nitrogen are again sent back to the converter, through this pipe, to join the converter to produce ammonia again, and the ammonia is cooled, taken out, the remaining hydrogen and nitrogen sent back again to the converter, so it's a continuous process. So this is the process, industrial manufacture of ammonia. Now, the reaction conditions such as temperature and pressure, they affect the rate of reaction. However, we're going to do a trade-off between the yield and the rate of reaction in this regard, looking at temperature and looking at pressure. Now, if the reaction is reversible, the position of equilibrium is always affected by the change in the conditions, and often we must consider the trade-off between the rate of reaction and the yield. We must consider a trade-off between the rate of reaction, that how fast the reaction is going, and what quantity of the yield of ammonia is produced. So we shouldn't concentrate on, oh, it's a fast reaction, we're making ammonia as fast as possible. We should also be considering the percentage of yield, how much percentage is manufactured of ammonia. So we have to look at both. Which factor increases reaction, rate of reaction, and at the same time also can increase the yield. Okay, if the factor is increasing the reaction, but it does not increase the yield, meaning it does not favor the forward reaction. Okay, this is the forward reaction. In this regard, the equation we wrote, this is the forward reaction. This fell. Nitrogen reacts with hydrogen to form ammonia. This is the forward reaction. And this forward reaction is exothermic. This forward reaction is what? Exothermic. The backward reaction is endo, because it's a decomposition reaction. The backward is an endo. This one is endo, because it's a decomposition reaction. Okay, this is endothermic. Endo. The backward is, or reverse. You use the word backward, endothermic. Either you say the backward reaction, or you say the reverse reaction. Okay, it's endothermic. But the forward reaction, which is which is hydrogen reacting with nitrogen, this forward one is called exothermic reaction. Now we look at the factor. Which factor favors the exothermic reaction, the forward reaction? Which factors favors the exothermic reaction? What should we increase? Which factor? Is it temperature or pressure or catalyst? Which one will favor the forward reaction? So these are the factors we want to describe or discuss as it were. Is that okay? Now we're going to look at the graph. Okay, the graph illustrates the effect of changing the temperature and pressure on the yield of ammonia, that is obtained. Now, following any of the curved line, we're going to look at, you have the first one, the topmost one, red, then green, blue, purple, pink, and then blue, purple. Okay, so you can see the color we have. Purple, the very high temperature. So at high temperature, the yield is not high, you see. So increasing the temperature, you don't increase the rate of manufacture of ammonia. Because you can see it's below. If you trace it here, the maximum value, if you trace it to the graph, you just get a like 15 or a little bit 20 something percentage yield. Okay? But here has a very high temperature. Meaning increasing temperature does not forward the rate of forward reaction. Does not forward the forward reaction. So meaning increasing the temperature in the Harber process, increasing the temperature to the maximum does not forward your yield. Although it may increase the rate of reaction, but it does not favor your yield. So it's not helping the yield. So what is manufactured? So you look here, the temperature is reduced to 500. Here you get a bit of more yield, but still it doesn't forward there, favor it. Here we have 400. At least here you can have a yield of about 40 or 40 something. You can have a yield of 40 to 43 or 40 to 45 yield. Okay, let's just say 42% yield. Here, the rate of reaction may not be too fast and it's not slow. And the yield is not too high, it's not too slow. So it's like a trade-off. It's like you are in the middle. Here, you reduce the temperature, the yield is good, but the reaction is very slower. You reduce to 330, yield is super perfect, because you get it over 60%, but the reaction is very slow. The reaction is very slow. So we have to look at all this. We also have to look at pressure. When we are increasing pressure, when we increase pressure, we also increase the yield. If you increase pressure, okay, you can see at 100 pressure, at 100 atmosphere, the yield is probably a certain number. At 200, the yield is has increased, right? The yield, percentage yield has increased. You can see up to this level. You got to this level for 450, the yield because for ammonia, for the Harber process, we use a temperature of 450 degrees Celsius. So this is what we use, the temperature of, and atmospheric pressure of 200. We use atmospheric pressure of 200 as a trade-off. It's not as if it's the best pressure we can use, but it will give you both a suitable yield and manageable temperature. Okay, a suitable yield and a reasonable fast rate of reaction. Okay, so this is what we use: a pressure of 200 atmosphere and a temperature of 450 degrees Celsius. Okay. Now we say by following any of the curved lines on the graph, it can be seen that the pressure increases, so too does the yield also increase at any given temperature. So if you increase the pressure, the yield will increase. So yield forward favors the forward reaction. Sorry, pressure favors the forward reaction, meaning it will increase your yield. Pressure is one of the factors that favors your forward reaction. So pressure is a factor we consider. Pressure. It favors your forward reaction. High temperature forwards your reverse reaction. Higher temperature forwards your reverse reaction. So you must, and reverse reaction means you are getting back your nitrogen and hydrogen, and you're not getting your ammonia. You are getting, so you shouldn't increase the temperature too much. You shouldn't increase your temperature too much, because when you increase your temperature, it will forward the decomposition of ammonia into hydrogen and nitrogen. So, but we must increase pressure to a reasonable level, up to 200 atmospheric pressure. 200 atmospheric pressure, a suitable trade-off. Okay, a best suitable trade-off for the pressure, which 20,000 kilopascal or 20 million-pascal. That's the atmospheric pressure we use in this regard. Is that okay? Now, let's take a look at other factors. Okay? Okay. Now, by following the vertical line upward from the x-axis, the graph shows that as the temperature decreases, that's your temperature is decreasing. If you're following up, you see the temperature as you go upward, temperature is decreasing. So as the temperature decreases, the yield actually increases. Yeah, we've already explained that. As this temperature is reducing, as you are going up, temperature is reducing. Your yield is getting higher because this is the yield axis. Your y-axis is the yield axis. So you can see the temperature is reducing as we are going up, and your yield is increasing. So as you reduce temperature, your yield increases. Meaning, if you are increasing temperature, it does not favor the forward reaction. It only favors the backward reaction. Do you understand? So it means when you are increasing temperature, you are actually favoring let's write the backward reaction. The backward reaction is that you have ammonia and you are decomposing ammonia. You are decomposing your ammonia. This is the backward reaction. For example, this is your ammonia. You are decomposing your ammonia. This is the backward or reverse reaction. To produce hydrogen gas plus nitrogen gas. So you are favoring this if you are increasing temperature. Meaning your yield, which is the ammonia, is going back to the original reactor. Remember, it's a reversible reaction. Right? Remember, it's a reversible reaction. This is a reversible reaction. So when you increase the temperature, it does not forward the it does not forward it does not favor the forward reaction. It favors the backward reaction when you increase the temperature. But when you increase pressure, it will favor your forward reaction. It will favor your forward reaction. From the graph, this is your yield. Okay? This is your yield. This is your yield. Percentage is going up. And this is your pressure. This is your pressure, atmosphere. This is your pressure. And the graphs are always like this. So we should have been using different color, right? Different color will be more stable. Okay? Okay? So here you have higher temperature, the one at the bottom, let's say 550. Here you have 500. Here you have 450. Here you have 400. There you have 350. Okay, so you can see as you are reducing your temperature, you are getting more yield. This higher yield. That's what I showed with the arrow. Like you are going, the yield is getting higher. Okay, you are reducing temperature, you're getting more yield. So higher temperature only favors backward reaction, the reverse reaction. Okay, but pressure is increasing this way, along this way. So increasing the pressure, you increase the forward rate of forward reaction. Because this is a question that can be asked in the exam. Which of these factors favors the forward reaction? The pressure. Okay, the atmospheric pressure favors the forward reaction, while temperature favors the backward reaction. Is that okay? Iron is used as a catalyst to speed up the reaction, but does not get itself does not get used up in the reaction. They are used as beds of iron catalysts. They are just beds, like beds of iron catalysts to just speed up the rate of reaction. Okay? Now the actual condition used must be chosen depending on the number of economical, chemical, and practical consideration that you have. Okay, the industry as a company, as a business, you will consider so many things. You consider your economic factors, how you make profit. You have to consider your raw material. You have to consider your chemicals that you have available, and you have to consider your practicalities, your practical applications. So for economic situation, we know every business wants to make profit. So you have to do it in a way that you maximize the yield of ammonia. You get more ammonia being manufactured. So you find a way to make sure more ammonia is manufactured. Because the system will reach a reversible state. It's an equilibrium reaction. So when it reaches the equilibrium, it can reverse. And instead of you getting ammonia, the ammonia will get decomposed to form hydrogen gas and nitrogen gas. So you must find a dichotomy, you must find a trade-off. Okay. Now, in the Harber process, the raw material we already mentioned, they are available and inexpensive to purify. Like the nitrogen you get from the air and the hydrogen you get from the natural gas. Okay. So all this, every business will consider the cost of getting the raw material and the process of processing them and making them ready for them to be put in the compressor to compress these two gas together and be sent to a converter to make them react together and produce ammonia. And then to be cooled in the cooler, and then the liquid ammonia will be carried and be sent to another tank to be stored as ammonia. Then they are used or they reconverted the hydrogen and nitrogen will be sent through tank, through pipes to the converter again to produce produce ammonia, further ammonia. Temperature that is chosen to produce an average level is 450 degrees. So we must remember these factors in the exam. The temperature is 450 degrees Celsius. So a higher temperature will favor the reverse reaction. We already mentioned this. If you increase the temperature more than this, you'll be favoring the reverse reaction, the reversible state. You'll be favoring the backward reaction. This one, you'll be favoring the decomposition of ammonia into hydrogen and nitrogen, not the forward reaction. Remember, this is the reverse reaction. We can write reverse here. Reverse. This is a reverse reaction. You are forwarding the reverse. We can use the word reverse or backward. It doesn't matter. It's the same thing. You are forwarding the reverse if you increase to temperature beyond 450. So you are forwarding the reverse reaction. You are actually getting ammonia, and you are actually getting more nitrogen and more hydrogen when you increase the temperature too much. But for the forward reaction, you have to reduce the temperature or bring it to an acceptable level in order to get hydrogen. This is the forward reaction. Hydrogen reacting with nitrogen, reacting with nitrogen to produce ammonia. I'm looking at each of the reactions separately. This is the forward reaction to produce ammonia. Produce ammonia. Okay? This is the ammonia that's produced. So you can balance this one up by putting 3 here and by putting 2 here. Okay. This is the forward reaction, this one. So we call it forward reaction. It's forward. Okay, it's not reverse. This is the forward reaction. So if too much temperature beyond 450 will not favor this forward reaction. If we say it does not favor forward reaction, it means that you cannot maximize the ammonia that is being manufactured. You cannot, meaning ammonia will be decomposing back to, like in this case, will be decomposing back to nitrogen and hydrogen. It's like a useless effort. You make ammonia turn back to your reactant again. So which is very bad. So that's why you do not choose temperature too high. So we designate the temperature to be 450 in order to maximize, to at least give a moderate yield of ammonia, to give reasonable yield of ammonia. So we leave the temperature at 450 degrees Celsius. Is that okay? To favor the forward reaction. Because if you increase the temperature too much, it will start favoring the backward reaction. It will be favoring the endothermic. The forward reaction is exothermic reaction, and the backward reaction is endothermic reaction. Okay, so that's that for that. Let's quickly move on. Okay, we say if a lower temperature is used, it favors the forward. See, reduce the temperature, lower the temperature, it will forward the forward reaction as it's exothermic. It's exothermic, so you don't need to raise the temperature too much. It releases heat and also give you higher yield of product, higher yield of ammonia. However, a lower temperature will affect the rate of reaction, make the reaction to be slow. That's why we have to choose a temperature not too low, not too high. If it's too high, if the temperature is too high, it starts to favor the backward reaction. If it's too high, it starts to favor the backward reaction. If it's too low, it becomes too slow that you don't get even good yield. So we chose something like a moderate temperature, which is 450 degree comparison. Okay? Now for pressure, 200 atmosphere is chosen. Now a lower pressure will favor the reverse reaction. If the pressure is too low, like 100, it will favor the reverse reaction. If the pressure is too low, it will favor the reverse reaction. As the system will try to increase the pressure by creating more molecules. You know, here we have altogether 4 molecules here. The reason why we need to increase the pressure. The reason why, let's go back to this already. Here you have 1 molecule of nitrogen, 3 molecules of hydrogen. Altogether 4 molecules in the reactant. Maybe we have to rewrite it. You have hydrogen, right? We have hydrogen plus nitrogen. Hydrogen plus nitrogen. Let's write the reversible state to produce ammonia. produce ammonia, NH3. Produce ammonia. Okay, we can balance the equation. Here we put 2. So hydrogen is now 6. So here we can put 3 to make it 6. So if you look at how many molecules we have on the reactant side, we have 4. There's 3 molecules here, right, for hydrogen, and 1 molecule for molecule is different from atoms. Atoms here is 6. 3 times 2, 6. I'm not talking about atoms. Atoms here is 2. But number of molecule here is 1. Number of molecule here is 1. Number of molecule here is 3. So molecule, there are 4 molecules in the reactant side. 4 molecules in the reactant side. Now in the product side, how many molecules? We have 2 molecules. I'm trying to explain why we increase pressure. Since the number of molecules in the reactor side is way higher than the number of molecules in the product side, you must increase the pressure. To favor the forward reaction, you have to increase the pressure. So anytime you have an equation, and you see the number of molecules on the reactor side is higher than the number of molecules on the product side, you have to increase the pressure in order to favor the forward reaction. So that's one reason, that's the main reason why we use the increased pressure. Okay? Increased pressure will favor the forward reaction because the number of molecules on the reactor side is higher than the number of molecules on the product side. Okay, so that's the scope for this. Now let's move on. So we have to increase the pressure in order. So a higher pressure will favor the forward reaction as it will try to decrease the pressure by creating less molecules. Okay, that's 2 molecules of gaseous product. So higher yield of product will be made. Okay, we've already explained this. Anyway, high pressure can be dangerous and is very expensive. So that's why we are not using, if you see, we have pressure up to 300 atmosphere, pressure up to 400. So why did we not choose 300 or 400 pressure? Since we say we should use increased pressure. That we say we should use increased pressure does not mean it's the best thing. It's just that you favor the forward reaction. If it's too high, the pressure is too high, it becomes dangerous. And it becomes dangerous. Safety is very important in the industry. So they took something reasonable that is safe. So 200 has been chosen because it gives you higher yield, it gives higher yields, and not also too dangerous. Because if you choose a pressure that is too high, it becomes dangerous. Okay, it becomes very, very dangerous. Even though it favors the forward reaction. Okay. And it's very expensive. Okay, the higher the pressure, atmospheric pressure, the more the cost. Remember, the industry don't want to spend too much so that they can make profit. So if they go and choose 300 atmosphere, that's too expensive for the business, for the industry, for the factory to manufacture ammonia. Ammonia gas will not be affordable. When they manufacture it, will be too expensive for us to pay for. Okay, so they have to choose a pressure that is good, is high enough, and is affordable. And also, if it's too high, it's not safe, it's dangerous, it becomes dangerous. Now let's take a look at why do we the iron catalyst. The presence of a catalyst does not affect the position of the equilibrium. It does decrease only the rate of reaction. Only it increases the rate of reaction, doesn't affect the position of the equilibrium. Why is this so? This is because the catalyst increases the rate of both the forward and the backward reaction. The iron catalyst will increase the rate of the forward reaction as well as the backward reaction. Increase both of them. Okay? By providing an alternative pathway requiring the lower activation, by lowering the activation energy. Okay? As a result, the concentration of the reactant and product is nevertheless the same at equilibrium as it would be without the catalyst. Okay? Without the catalyst, it will more or less be the same, but with catalyst, it's not going to be the same. Catalyst speed up the rate of reaction. So a catalyst is used to help the reaction to reach equilibrium faster. A catalyst is just something used to help the substance to reach its equilibrium faster. Is that okay? So that's all we have for our today's class, explaining the manufacture of ammonia using the Harber process. Okay, so thank you for joining us.